Hello and welcome to our series of videos on the AQA A-level Chemistry Paper 3 or Component 74053. This video is focusing specifically on the 2022 Paper 3 and I'm going to be talking through the multiple choice questions. You'll find when you're marking your answers to multiple choice questions it will tell you what the answer is, but there will be no explanation as to how to get there. So this video is hoping to explain each of those questions to you. Adding timestamps in, so if there's a specific question you're not sure of, you can skip forward to that question and just listen to that explanation. Alternatively, you might want to work through the whole set of multiple choice questions and then just listen to the explanations to the answers afterwards. Starting off with question 6, which atom in the ground state contains at least one unpaired p electron? So remember the p sublevel contains 3 p orbitals. P can hold up to 6 electrons. So sodium is in the S block, it's in the third period. So 1s2, 2s2, 2p6, 3s1. Neon is in the second period at the end of the p block, ends in 2p6. Oxygen is in the fourth column of the p block, so that's 2p4 it will end in, and scandium is in the D block, ends in 3p6, 4s2, 3d1. Remember 4s2 is filled, 4s is filled before 3d. So oxygen has an incomplete p sublevel. Why is there an unpaired p electron? Well, when electrons are filling the p orbitals, they will be unpaired before they are paired up. So oxygen has 2 unpaired p electrons, as we can see here. Answer C is correct. Question 7. Complete combustion of 0.01 moles of an organic acid. So we've got an organic acid here, 0.01 moles, reacting with oxygen is going to produce CO2 and water. And it produces 0.02 moles of carbon dioxide. The same amount of acid required this much sodium hydroxide for neutralization. So starting off, the fact that you have a 1:2 ratio of the carboxylic acid to CO2 implies that there must be 2 carbons in the carboxylic acid. So it must be either ethanoic acid or ethane dioic acid, due to the 1:2 ratio of the carboxylic acid to CO2. So it's either going to be answer B or C. Answer A would produce a 1:1 ratio with CO2, and answer D would produce there are 3 carbons, a 1:3 ratio with CO2. So which one of these? We need to use the second bit of information to determine which acid is present. So you can work out the number of moles of NaOH using concentration and volume. So we've got concentration is 1, volume is 20 centimeters cubed, converted to decimeter cubed. So we have a molar ratio there of 0.02 moles of NaOH. So if there's 0.02 moles of NaOH and 0.01 moles of the acid, that suggests that the NaOH to the acid must be diprotic in order for it to react with twice as many moles of NaOH. So it must be a diprotic acid, must have 2 carboxylic acid groups. Answer C is correct. So question 8, which substance has no delocalized electrons? So graphite has delocalized electrons between layers. Each carbon forms 3 bonds. There is a delocalized electron per carbon atom. So that does have delocalized electrons. Methyl benzene, you've got the benzene ring. Benzene ring has a ring of delocalized electrons. Sodium is a metal. So if it's metal, it's going to have metallic bonding, which is where you have your positive metal ions surrounded by a sea of delocalized electrons. Polypropene is made from propene. It's an addition polymer. There's just single carbon-carbon and carbon-hydrogen bonds there. And that's your repeat unit. So polypropene has no delocalized electrons. Question 9. Consider the change that occurs in the shape of the curve for the distribution of molecular energies in a gas when the temperature is increased. So this is your Maxwell-Boltzmann distribution. So very rough version of the Maxwell-Boltzmann just drawn below at a higher temperature. So when you increase the temperature, the curve gets flatter and moves to the right. Something like that. So which is a correct statement about the gas molecules at a higher temperature? There are more molecules with any given energy. Well, that's not correct because you can see the curve gets flatter, so there are fewer molecules with certain energies. There are more molecules with the mean energy. So the mean energy is just to the right of the peak. I've just put a dot on there. Because the curve gets flatter, there are actually fewer molecules with the mean energy. Similar to statement B, there are more molecules with the most probable energy. Well, the most probable energy is the top of the peak. And because it gets flatter, there are fewer molecules with the most probable energy. However, there is an increase in the most probable energy. So remember, energy is on the x-axis, number of molecules is on the y-axis. Because the peak moves to the right, the most probable energy is increased. Answer D is a correct statement. Question number 10. Which of these oxidation states is correct? So when it says which of these answers, you have to go through all of them to make sure you've checked all of them. So in chlorine, which is an element, an uncombined element, the oxidation state is 0. In potassium dichromate, just write this below, K2Cr2O7, each oxygen is -2, so that gives us a -14. Potassium is +1, so that gives us +2 for the potassiums. So that means if you've got -14 and +2, the chromiums must add up to +12. That means each chromium is going to be +6, not +7. Fluorine in F2O is -1. Well, fluorine is always -1 when it's in a compound. Because it's more electronegative than any other element, it's always going to become -1. So answer C is correct, so let's just eliminate answer D. Hydrogen is normally +1, but because it's bonded to a metal, that's the exception to the rule, hydrogen has an oxidation state of -1 with metal hydrides. So answer D is incorrect. Question 9. Which change to a hydrogen electrode has no effect on the electrode potential? So in the hydrogen electrode, you have hydrogen ions in solution, and you're making hydrogen gas, or hydrogen gas is bubbled in. So in order to shift the position of equilibrium, you can change any one of the concentration of H+, change the pressure because we have hydrogen gas, and you can change the temperature. Temperature affects the position of equilibrium. So these three things affect the position of equilibrium, therefore would affect the electrode potential. So going through the answers, that would have an effect because you're changing the concentration of H+. The pressure would cause it to shift. The temperature would cause the equilibrium to shift. The surface area of the platinum electrode. Platinum electrode is just a surface for the reaction. So that would change the rate of reaction, but it would have no effect on the position of equilibrium. So therefore it would not affect the electrode potential. So C is an incorrect statement. Question 12, some electrode potential data are shown. What's the correct statement about this cell? And it gives you the cell diagram. So when a cell diagram is given to you, the electrons are going to flow from left to right, provided the substance on the left, the substance at the anode, is more negative or has a more negative electrode potential than the substance on the right at the cathode. So let's just check, does zinc have a more negative electrode potential than lead? It does. So electrons are going to travel from left to right. The anode is where oxidation occurs and the cathode is where reduction occurs, provided it's set up the correct way round, which it is. So as the electrons flow from left to right, the zinc is oxidized to Zn2+. The lead ions are reduced to lead solid. So the concentration of lead ions will not increase. The lead ion concentration will decrease. The maximum EMF of the cell, the maximum electromotive force or electrode potential, would be 0.89, or let's just work that out. E values can be calculated by doing reduction minus oxidation, or right hand electrode minus left hand electrode. So right hand electrode is minus 0.13 minus 0.76. Sorry, brackets in the wrong place there. Right minus left will give us an EMF of plus 0.63 volts, not 0.89 volts. And just finishing off by eliminating statement D, zinc is deposited. Well, zinc is not deposited. Zinc, as we've shown, is oxidized into zinc 2+ ions. So that statement is incorrect. Statement A is the only correct statement there. Question number 13, which cannot function as a Bronsted-Lowry acid. So remember, Bronsted-Lowry acid is a proton donor. So which one is unable to donate protons? The answer is A, which I'll explain in a second. B, you've got the hydrogen carbonate ion. Well, you should know that you can also have the carbonate ion. So that is able to donate a proton. H3O+, well, is that able to dissociate with a proton? Yes, it can. It can form water and hydrogen ions. And in fact, this equation is happening in water all the time. And ammonium, you should know, can exist as NH3 ammonia. And so it can donate the H+. So all three of those answers, B, C and D, can act as acids because they can all donate protons. The ethanoate ion that you can see here, it's got your CH3 C double bond O, O-, has already donated a proton. It cannot donate any of these protons because the CH bond is very strong. So it's already acted as a Bronsted-Lowry acid. It cannot donate any more protons. It can act as a Bronsted-Lowry base. It can accept a proton, but it cannot donate a proton. So A is the correct answer here. Question number 14. A strong acid dissociates into an aqueous solution, and you're given the equation. What's the pH of this solution of the acid? So if you have 0.02 moles per decimeter cubed of the acid, that means you're going to have twice as many moles per decimeter cubed of the hydrogen ions. So if you've got a concentration of 0.04 moles per decimeter cubed, because it's a diprotic acid, minus log the concentration of H+, so minus log 0.04, that gives us the pH, which we can see as 1.3979 or 1.40, rounded to 2 decimal places. Question number 15. Equal volumes of two solutions, each with the same concentration, are mixed together. Which one's going to form a solution with a pH of greater than 7? So which one will have an alkaline pH? Just to highlight the top bit that I've underlined, they've got equal volumes, equal concentrations, so the moles of the mixtures are going to be the same. It's going to be equimolar. So let's work out which substances we have. In statement A, what we have is an acid, it's methanoic acid, and it's salt. So when you mix those two together, you're going to have a pH of less than 7. Statement B, you have a strong base and a weak acid. So in this case, you're going to have a pH of greater than 7. Remember, on the pH curves of a strong base and a weak acid, the equivalence point, when you've got equal number of moles, the pH is around 9, so the pH is greater than 7. The statement or mixture B is correct. Just go through C and D just to eliminate those answers in case you weren't sure about those. So NH3 and HCl, you're going to have a weak base and a strong acid. So again, the pH is going to be less than 7 when you mix those together. And finally, you've got ammonium chloride and potassium chloride, which are both salts. They're not proton donors or acceptors, they're not acidic or basic, so the pH is going to be about 7, depending on the temperature. So statement B or mixture B, strong base, weak acid, equivalence point greater than 7, so therefore B is correct. Question 16. Which ionisation needs less energy than this process? So this process is representing the first ionisation for magnesium. So you looked at first ionisations in a number of topics, but you came across it first in the atomic structure topic. So going across the period, from to the period 3, you've got sodium, magnesium, aluminium, then you have silicon, phosphorus, sulfur, chlorine and argon. So which one has a lower ionisation energy than magnesium's first ionisation energy? Well, it's not going to be D, because that's the second ionisation energy. Ionisation energies will always increase if you're removing more than one electron from an atom. It's not going to be beryllium, which is also in group 2, but beryllium is a smaller atom, it's got less shielding than magnesium, so it would require, or it would have a higher first ionisation energy. It's not going to be argon. First ionisation energies generally increase across a group, so it's not going to be argon because that's got the highest in period 3. So aluminium's first ionisation energy is lower than the first ionisation energy of magnesium, which we can see here, and that's because its outer electron is in the p orbital, which is in higher energy or further from the nucleus than magnesium's outer electron, which is in the 3s orbital. So aluminium has a lower first ionisation energy than magnesium. Question 17. Which statement is correct about the group 1 elements? So again, if it's asking about statements, you need to go through each one, eliminating the ones that are incorrect. So the cesium ion has a more negative enthalpy of hydration than the rubidium ion. So looking at the periodic table, looking at the group 1 elements, rubidium is higher than cesium. So rubidium is a smaller ion. If it's a smaller ion, it's going to be more strongly attracted to water, so it's going to have a more negative enthalpy of hydration than cesium, so that statement is incorrect. Enthalpy of atomization for potassium. So what is atomization? You're forming 1 mole of gaseous atoms from the element in its standard state. So which one is going to require more energy to turn into gaseous atoms? It would be the smaller atom, because when it's in its standard state it has metallic bonding. The smaller the metal, the stronger electrostatic attraction between positive ions and delocalized electrons. So the smaller the atom, the greater the atomization enthalpy. So potassium is greater than sodium, or potassium is a bigger atom than sodium, and therefore potassium would be less than that of sodium. So that is an incorrect statement. Similarly, the melting point of potassium is higher than the melting point of sodium. So these two answers are kind of linked together. You're breaking apart the metallic bonds. Sodium has a higher melting point than potassium because it's a smaller ion, stronger metallic bonding. That statement's incorrect. Hopefully statement D is the correct statement. So lithium's second ionization energy, so lithium plus to lithium 2 plus in a gaseous state, is going to be more positive than the second ionization energy of rubidium. Well, rubidium is lower down the group, so rubidium is a bigger atom or bigger ion, therefore rubidium has more shielding. So the second ionization energy of rubidium would be less than the second ionization energy of lithium. Statement D is correct. Question 18. Test for chloride ions in aqueous solution involves adding dilute nitric acid followed by silver nitrate. Why do you add the nitric acid? So you must always acidify the solution before adding silver nitrate. And the reason is silver complexes or silver ionic compounds are often insoluble. So you need to add nitric acid because the H plus ions will react with any ions that would form a precipitate with silver. So for example, silver would react with hydroxide ions to form silver hydroxide, precipitate, don't need the brackets there, or it will also react with carbonate ions to form silver carbonate precipitate. So the hydrogen ions will remove any hydroxide ions and carbonate ions. Won't form that complex there. It's got nothing to do with the solubility of silver chloride. We're trying to form the silver chloride precipitate, so that's an irrelevant statement. It wouldn't increase the pH of the solution, but that's again wouldn't affect the formation of the precipitate. It would in fact decrease the pH. And statement D is correct, to prevent the precipitation of other silver compounds. Question 19. Which pair of reagents react to form a tetrahedral complex? So tetrahedral complexes occur when the ligand is too large, and therefore normally you get 6 ligands or 6 coordinate bonds. If it's 6 coordinate bonds, then it's going to be octahedral. If the ligand is too large, you can only fit 4 around, and that occurs when you have chloride as a ligand. So you get 4 chloride ligands bonded, that forms a tetrahedral complex. So looking through here, which one has chloride as ligands? These 3 would all form octahedral complexes. You've got 6 NH3s, or you've got 3 of the ethane dioates. Ethane dioates, remember, is a bidentate ligand, so they would all form octahedral complexes. HCl, concentrated HCl, would form 4 chloride ligands. That would form FeCl4, and that is 3 plus charge, so it would be a negative complex overall. That would be tetrahedral. Question 20. Cobalt chloride solution changes colour when an excess of concentrated hydrochloric acid is added. So cobalt 2 chloride, COCl2, aqueous, will actually exist as the hexa aqua cobalt complex because it's a solution. Solution means water is in excess, it's aqueous, lots of water present. That's going to be the main complex present. By adding concentrated hydrochloric acid, just like in the previous question, you're adding 4 chloride ligands, so you're going to get COCl4 as the main complex forming here, and 6 waters. So what's happening? The 4 chloride ligands are swapping for the 6 water ligands. That is a ligand substitution reaction. Question 21. The reaction between vanadium ions and manganate 7 ions in acidic solution can be represented by the equation. What volume of KMnO4 is needed to oxidize this many moles of vanadium-4 completely? So you're told the moles of vanadium-4. 0.1 moles. So if you had 0.1 moles of vanadium-4, how many moles of manganate would you need? You can see here it is a 5:1 ratio of vanadium to manganate. So we need to divide that by 5 to work out the moles of manganate. 0.1 divided by 5 will give us the moles of manganate being 0.02. What volume of manganate is needed? Well, to work out the volume of manganate, you do moles divided by concentration. So 0.02 moles divided by the concentration, which tells us in the question, which is also 0.02. So that's going to give us a volume of 1. If the volume is 1, then that means in decimeters cubed, answer C is correct. Question 22. 2-bromopropane reacts with bromine to form 2,2-dibromopropane. So we're going from a haloalkane. I'll just draw that in there. That's your 2-bromopropane reacting with bromine to form dibromopropane. So haloalkanes, the haloalkane bond isn't breaking, the CBr bond remains intact as we can see here, and we're breaking a CH bond to make a CBr bond. The CH bond is usually inert, needs something fairly reactive to break that bond, and that was going to be a free radical. So this type of reaction happens is free radical substitution. Question 23. Which compound is formed when bromoethane reacts in a nucleophilic substitution reaction? So nucleophilic substitution occurs when your haloalkane reacts with potassium cyanide, sodium or potassium hydroxide, and excess ammonia. So if we react it with KCN, you're going to form propane nitrile. The CN substitutes in, the bromide breaks off, so you're going to get propane nitrile, CH3, CH2, CN. So there's not enough carbons in A, so A is incorrect. So B, the product here is ethylamine. The NH3 acts as a nucleophile, attacks the delta positive carbon, the bromine breaks off. You're going to get ethylamine as the product. The extra NH3 removes one of the hydrogens, so that is correct. Just go through C and D just to eliminate those as answers. So haloalkanes will also react with potassium or sodium hydroxide under reflux when the hydroxide is dissolved in ethanol. The hydroxide acts as a base and therefore it will form ethene. That's not nucleophilic substitution, that's elimination. So this will form from bromoethane, but it's by elimination, not nucleophilic substitution. And finally D, you've got ethyl hydrogen sulfate forming. That's formed between an alkene and sulfuric acid in an electrophilic addition reaction. So that one's also incorrect. B is the only product that will form by nucleophilic substitution out of the options given. Question 24. Which statement is not correct for both primary and secondary alcohols? So going through, primary and secondary alcohols are not easily oxidized to carboxylic acids. Only primary alcohols are easily oxidized to carboxylic acids. Secondary alcohols will be oxidized to ketones and will not be further oxidized. So statement A is correct. Just go through statements B to D to remove those and show you why they are correct. So they can be formed from bromoalkanes by hydrolysis. So if you have a primary haloalkane or primary bromoalkane, if you've got hydroxide ions present, hydroxides act as a nucleophile, the CBr bond is broken to hydroxide, hydrolyzes the CBr bond, you will get a primary alcohol formed if it's a primary haloalkane. If it is a secondary haloalkane, so you've got another R group there, the same thing happens and you'll get a secondary alcohol formed instead. So that is a correct statement. They will form esters with carboxylic acids. Yeah, primary, secondary and tertiary alcohols will react with carboxylic acids in the presence of sulfuric acid to form esters. And do they show hydrogen bonding? They both have OH bonding, OH bonds. It's a very polar bond because the oxygen is very electronegative, more electronegative than hydrogen. And so you will get hydrogen bonds between the delta positive hydrogen on one alcohol and the delta negative oxygen lone pair in another alcohol. So they both show hydrogen bonding regardless of what type of alcohol it is. So again, statement A is incorrect. Question 25. Which compound is an isomer of ethyl ethanoate? So ethyl ethanoate has this formula here. What's the overall formula for that? Well, you've got 4 carbons, you've got 2 oxygens, and you have 8 hydrogens there as well. So which of these esters is going to have 4 carbons in? So butyl methanoate, it's got 5 carbons, it can't be butyl methanoate. Methyl propanoate, you've got CH3, CH2, COO, so you've got prop, which has 3 carbons, and then the methyl group, which has a carbon. So methyl propanoate is an isomer of ethyl ethanoate. Methyl butanoate, just like A, has got 1 too many carbons in. You've got meth and bute. So you're going to have 5 carbons there. That's not an isomer. And finally, propanoic acid just has 3 carbons in, not 4 carbons. So the only one with 4 carbons and the same formula as ethyl ethanoate, the only one that's an isomer, is compound B. Question 26. Which compound is an amide? So remember, an amide has a C double bond O and an NH2, or a C double bond O and an N, and the H's can be replaced by R groups. So for example, that one there. So going through, A is a nitrile, B has a CONH, so that looks like it's an amide. Let's just check the other ones. C is an ester, and D is a secondary amine there. So it's not got the C double bond O group, so it's an amine, not an amide. So compound B, which is N-ethyl ethanamide, is the only amide out of the 4 options given. Question 27. This compound here is commonly used in the manufacture of polymers. So you've got COCl on both sides. So you have a diacyl chloride. diacyl chlorides can form polymers by reacting with diamines, so where you've got your NH2 on each side of the compound, or diols, where you've got hydroxy or OH groups on each side of the carbon chain or the R group. So which compound will react with the diacyl chloride? Well, it's going to be a diamine or a diol. So A is correct. Let's just go through the others. That's also a diacyl chloride, so that won't react. That is an amide. It's only got one amide group as well, so that's not going to form any type of polymer. And this is a dicarboxylic acid. They both have C double bond O groups, so that's not going to react with a diacyl chloride. So to form a condensation polymer, you can have diacyl chlorides reacting with diamines to form polyamides, or diols to form polyesters. Which polymer is not hydrolyzed when heated with aqueous alkali? So polymers that are hydrolyzed means they are biodegradable. The reason they're biodegradable is because they have polar bonds. And so condensation polymers are biodegradable. Type of condensation polymers you've come across are polyesters and polyamides. So Kevlar and nylon are both polyamides. They are both biodegradable. They will both be hydrolyzed in the presence of sodium hydroxide or an aqueous alkali. Terylene or PET is a polyester, so that will also be hydrolyzed. Polypropene is an addition polymer. Addition polymers do not have a polar bond or polar bonds. They are not biodegradable, so they can't be hydrolyzed. So C is the one that will not be hydrolyzed. Question 29. Which is the main species present in an aqueous solution of aspartic acid at pH 14? So it's an alkaline environment. This is almost identical to a question in the 2018 paper 3, but the structure of the amino acid is arranged differently. So if you've got a high pH with amino acids, you've got an excess of hydroxides, ions, and a lack of H+, or an absence of hydrogen ions in the solution. So what will happen is the COOH groups in an alkaline environment will become COO-. The amine group, which can exist as NH3+, but there's a lack of H+ in the solution, so the amine group remains as NH2. So at a high pH, both of the COOHs become COO- in aspartic acid, and the NH3 remains as NH2. So therefore answer D is correct. Question 30. Which type of reaction is not involved in this reaction sequence? So going across each of these, I'll just talk through the type of reaction. So you have a benzene ring for step 1. You're adding an NO2 group. So that is a nitration reaction. Nitric acid is used in the nitration reaction with concentrated sulfuric acid. So nitration is involved in this reaction sequence. The COCH3, that's a ketone group, is going to an alcohol group. So what's happening in reaction 2 is a reduction reaction. That occurs with NaBH4, for example. So reduction is occurring here as the ketone is reduced to a secondary alcohol. In reaction 3, our alcohol is reacting with a C double bond O group which we can see here. It's reacting with a carboxylic acid. So in reaction 3, carboxylic acid plus alcohol is an esterification reaction. So the one that's not occurring is hydrolysis. Answer B is correct. Question 31. Which pair of reagents does not produce ethanol? So answer A, you've got a haloalkane plus aqueous sodium hydroxide. That'll be nucleophilic substitution. The OH swaps for the bromide, so you're going to get ethanol and sodium bromide forming. B, you have an ester plus sodium hydroxide, so that is ester hydrolysis. And in ester hydrolysis, in the presence of an alkali, you're going to get the carboxylic acid salt, so you get sodium methanoate, and you get the alcohol. So in this case, the alcohol is CH3, so you're going to get methanol, not ethanol. So it looks like B is going to be the correct answer. Let's just eliminate questions C and D. So in question C, again, it is ester hydrolysis, because you have an ester reacting with sodium hydroxide. You're going to get the carboxylic acid salt, sodium methanoate, and the alcohol here is 2 carbons in length, so you will get ethanol in the second ester hydrolysis. And finally, D, you've got sodium borohydride reacting with an aldehyde, so you're getting reduction of an aldehyde, so you're going to form your ethanol by reducing an aldehyde. So answer B is the only one that would not produce ethanol because it produces methanol instead. Question 32. Which type of interaction between polypeptide chains is mainly responsible for maintaining the secondary structure of a protein in the form of an alpha helix? So remember your different types of structures for protein. Your primary structure is the sequence of amino acids. Your secondary structure of a protein is the hydrogen bonds between the amino acids. That usually occurs between the NH groups of the polypeptide chain and the CO groups of the polypeptide chain. So your secondary structure in alpha helices and beta pleated sheets, for example, is hydrogen bonding. Tertiary structure is the further folding of protein, and that's usually the interaction between R groups. So that's where you're going to get your ionic interactions, your disulfide bridges, your van der Waals forces, and your dipole-dipole forces. So secondary structure is the hydrogen bonding between your polypeptide chains. Question 33. Which statement about this molecule is correct? So I'll just draw this molecule out. So you've got your CH2, CHCOOH. On the CH you've also got an NH2, and on the CH2 you've got an alcohol here. So this is in fact an amino acid. So you can see here you've got your amine group, you've got your carboxyl group, and this is your R group. So let's go through which ones would react or which statements are incorrect. So would it decolorize bromine water? Bromine water decolorizes in the presence of alkenes. There is no C double bond C. So that statement is incorrect. Is it a component of DNA? No, it's not a component of DNA, but it's a component of proteins instead. Is it insoluble in water? Well, you should be aware that amino acids are water soluble. They exist as Zwitter ions when they're on their own, and the ions are soluble in solution. Will it react with hydrochloric acid? So does it have any group that could react with an acid? The NH2 group has a lone pair of electrons. It would react with hydrochloric acid because the NH2 group is basic, so you'll get NH3Cl. Statement D is correct. Question 34. Which compound can be dehydrated to form an alkene? So dehydration means the removal of water. So if you're removing water, the way dehydration works is you remove an OH from one carbon and an H from another carbon, from an adjacent carbon, to get your carbon-carbon double bond. So dehydration will occur in alcohols only. So the dehydration of ethanol, this occurs in the presence of concentrated sulfuric acid, about 180 degrees Celsius, will form ethene. The other ones will not be dehydrated. And finally, question 35, which is not a 2-amino carboxylic acid, which is not an alpha amino acid. So remember, carbon 1 is where the COOH group is. So compound A has the amino group on carbon 2. It is 2-amino, 3 carbons in length, propanoic acid. Compound B, the amino group is on the 3rd carbon where the COOH is. So that's 3-amino butanoic acid. So that's not a 2-amino carboxylic acid. Let's just go through C and D just to eliminate those. So this one is 2-amino butanoic acid, because NH2 is on the 2nd carbon. And the final one is 2-amino. It's got a methyl group on carbon 3. 2-amino, 3-methyl butanoic acid. So again, that is also a 2-amino carboxylic acid. So answer B is the only one that is not. So this brings us to the end of the Paper 3 2022 multiple choice questions. If you'd like further clarification on any of the answers I've been through, please do leave a comment and I'll get back to you as soon as I can. Otherwise, best of luck with your exams. I hope they go well.